right, I think I'm going to go ahead and get started. So if you guys can quiet down, please. All right, so today, on my syllabus I mentioned that we were going to have another day of synthesis, but I think it's probably better if I go ahead and I start carbonyls. It might take me a couple days to go through carbonyls, and I think that'll open up down the road for us to do more synthesis problems that are more involved with more of the reactions. So I am going to sort of jump ahead one day in terms of the syllabus and sort of go to carbonyls. And so carbonyl chemistry, right, when I'm talking about carbonyls, this is still in line with sort of pi bonds, right? So you sort of have your alkene, right? Carbonyl is any molecule with a carbon double bonded to an oxygen, okay? And so as we'll see, there's different names that you can call these. Ketones refer to carbonyls where you have a carbon here and a carbon here. We'll often refer to things called aldehydes where you have a carbon here and say a hydrogen here. There's things called esters, which are a carbon here and an oxygen there, OR. And so you're going to hear some terms that are going to be used on occasion that refer to different carbonyl-containing molecules. So it's probably best that you learn those because we will talk to them. And there are differences between the reactivity of these different carbonyls. So as we start getting further into carbonyl chemistry, we will sort of see those and those sort of differences will bear themselves out. I want to introduce carbonyl chemistry a little bit like alkene chemistry because I think that there are some similarities, and I think it's best, again, when you're learning something new to sort of relate it to something that you've seen in the past. So if I go ahead and I take and I make this unsymmetric alkene that I've shown here, right, there's a resonance form that we can draw on this, right? And so when we start to talk about alkenes, we talk about a resonance form, right? And of the two possible resonance forms, the one that is perhaps more appropriate, right? Obviously, this is the best resonance form, but if we're going to sort of draw this resonance form that might illustrate the reactivity, you would have a mechanism with that, but you would want to put the negative charge onto the terminal carbon, and on the sort of more substitute carbon, you would put the carbocation, right? And so oftentimes what we'll do is we'll put a delta minus to sort of reflect that carbon can bear a partial negative charge, put a partial positive charge there, and again, this sort of represents how the dipole of an alkene might be. So it turns out that when you get to carbonyls, you actually even have a more extreme version of this, right? Because what you can imagine is a resonance form in the same way, right? You can imagine two resonance forms, and I'll draw them both just to sort of make this clear, right? But we can draw one resonance form that looks like that, right, where we push those electrons that way, right? And so that would be this resonance form. Alternatively, we can go the other way. Right, and so as you sort of look at these two resonance forms, you might ask the question, or I might ask you guys the question, which one of these might seem to be happier, right? Of these two possibilities, which one do you guys think would more... Right, so and the reasons for that are, right, that oxygen is more electronegative, so oxygen is more likely to bear this negative charge. And as we'll see, there's some other factors that are in play for this as well. So it turns out that as we're thinking about the resonance forms of a carbonyl, sometimes as a first step, as you're trying to get to know carbonyl chemistry, a lot of the chemistry that we'll talk about can sort of be thought of through this resonance form. So certainly this is the more stable resonance form, right? The carbonyl, all the octets are filled and everything else. There's no separation of charges. This is something we've discussed down the road. But this resonance form here, while it's a minor resonance form, it might help us think about how the reactivity takes place in carbonyls. So again, if we were to draw a delta positive, that delta positive would be at the carbon of the carbonyl, and we could put a delta negative over on the oxygen part of here. And that's just going to help us think, about how some of the chemistry might take place. Okay? So using this sort of knowledge, So we can go ahead and sort of learn our first reaction of carbonyl chemistry, and in many ways this is going to be analogous to what we've seen in the past, right? So if you went ahead and you took, these are just going to be more general reactions, right? If you went ahead and took this carbonyl, right, and you treated it with, say, a nucleophile, right, a really strong nucleophile, you can get these nucleophiles to react with the carbonyl. And so the question is, how would it react, right? And so when you sort of look at this resonance form and you look at the positive charge, when this nucleophile attacks this carbonyl, where's it going to attack it? On the carbon, right? And so we can think about a mechanism. You can either go through the minor resonance form, so you can either draw the resonance form and draw it attacking, or alternatively, what we'll normally do is we'll do sort of two arrows, right? And what we'll get here is a new bond between that nucleophile and the carbonyl carbon. And you basically transfer that negative charge onto that oxygen. So when you attack that carbon, you're going to not want to have 5 bonds here, right? So you're going to push those electrons onto that oxygen. Conservation of charge, now you end up with the oxygen there. In general, what happens is at the end of a reaction, right, you'll do a workup. And so when you do a workup, say with water, so you have charges with a whole bunch of water, what's going to happen is you're going to propane this. Okay, and so what you're going to see from time to time is that we're going to take carbonyls and we're going to react them with some nucleophiles. These are the reactions that we're going to see from time to time. And the result is that we're going to form a new carbon-carbon bond, right? And then we're going to have an alcohol. Okay, so this is one of the first types of reactions. This is just a sort of a general thing that we're going to see about nucleophilic species reacting with carbonyls. Okay? Alternatively, right, the other thing that sometimes we'll see as we're talking about carbonyl chemistry is we can take these molecules. The other thing that we'll see from time to time, and I won't show a full reaction, but this is just to sort of get you guys thinking from a mechanism standpoint. If we want to take this and instead of treating it with, say, a nucleophile, right, we want to treat this with an acid, right? And so I'll just sort of say acid. And what I'll do is in the same way that I sort of said nucleophile, I'll just sort of write acid there. And so what we could be referring to is something like a Bronsted acid where we have H+, right? Or we could have, say, a Lewis acid, say BF3, right? But the point is that we've got some sort of an acid source. What's going to form the bond with that acid? The oxygen, right? Right, and so what's going to happen is when you react this with either a Lewis acid or a Bronsted acid, the acid's going to form on the oxygen. So again, the nucleophile is going to attack the carbon. If you treat it with some sort of an acidic source, it's actually going to react with the oxygen. Okay, and in this case, we can draw one of two resonance forms. Right, so we'll often draw it this way, but certainly at this point you can imagine another resonance form. Right, and again, this is going to be the major resonance form. Why? Full octet, right? But as we'll see, this could be a resonance form in the same way that we saw before, where sometimes it's this resonance form that will actually help explain the subsequent chemistry that we're going to see. Okay? So again, a theme going forward with carbonyls is going to be these two sorts of reactivities. You treat a nucleophile with a carbonyl, you're going to form a bond with the carbon, right? And then so on and so forth. If you treat it with an acid, right, we're going to basically react with the oxygen, and that's going to sort of be somewhere in this sort of this molecule. Again, those are just two resonance forms representing the same thing. Okay, so this is going to be the chemistry of carbonyls. We're going to learn some new reactions with these carbonyls, but by and large, we can think about them through this sort of thought process. Okay? So, all right, so okay, so let's just do a quick reaction to think about. Again, you've never seen this reaction before, but we'll sort of ask ourselves what the product of this reaction might be, just to sort of get our sort of wheels turning. Let's say that we took acetone, right? And let's just from a mechanistic standpoint, imagine that we took acetone and treated it with cyanide, okay? So HCN. So cyanide is acidic. We can imagine a couple different ways of this taking place, but I think that we might be able to rationalize a mechanism of how a ketone might react with cyanide, okay? So what do you guys think would be the first step of this reaction? Yeah. Right, so what we're going to do is we're going to have the oxygen attack the hydrogen. We're going to break that CN bond. Okay, and then what's left over is a CN minus. Okay, and then what's going to be the second step? All right, the CN minus is going to attack that carbonyl. Right, and what you're going to end up with is a molecule whereby you have cyanide adding across a carbonyl. Okay, so it's analogous in many ways. This one's very analogous to, say, HBr across an alkene. But this is, again, just cyanide adding in to an alcohol. Okay, so this is an example of a reaction with a carbonyl that I think reflects the chemistry that we've seen over here. Okay, so now it turns out that this represents one of the more simple reactions from a mechanism standpoint. A lot of times the carbonyl reactions from a mechanism standpoint become a little bit more involved. Okay, and so what I'm going to show you next is a reaction, but it sort of all bears in mind here. Okay, so the next reaction I want to show you guys is going to be sort of, I'll break it down into two steps. So I'll start making this something a little bit simpler, just in terms of the first step, and then we'll actually see that this pushes a little bit further. But if you take a ketone or you take acetone and you treat it with sulfuric acid, okay, and you do this in the presence of, say, methanol, okay, the first question I want to ask you guys is maybe not necessarily the finished product, but doing an analogous reaction to what we saw up here, at least sort of the first step, what might be the product that might form? So I want you guys to sort of think about that for a second as I erase this. All right, so if we take acetone, treat it with an acid, and methanol. So what's going to be the first step in this reaction? So what's the strongest thing in this reaction? Right? Sulfuric acid, right? So the sulfuric acid is a strong acid. We've seen this time and time again. So anytime you see a strong acid, that's probably the first thing that you should do is try to do a reaction with that acid. So we're going to do the same thing we did with the cyanide, right? We're going to react, generating that sulfonate. Okay, and now what might you guys think is going to be the second step? Methanol. So this is almost identical, right? Yeah, I mean this is almost identical to, you've seen a very similar reaction, right? We've seen a very similar reaction with alkenes, right? So we saw acid and methanol. We'll add methanol across an alkene double bond, right? Now, one of the things here, though, is that in the case of alcohol chemistry, things get a little bit different. And that's because of some of the reactivity of these. Okay, so let's just complete this mechanism really quickly. Okay, so what might be the next step in this reaction? Right? We're probably going to maybe we're going to deprotonate that, right? And so we can do that. Again, anything, we could have the methanol do that. We could have the sulfonate do that. We'll just do the sulfonate here just to keep things sort of balanced. Okay? And so what you might expect to get is this molecule here. Okay, so you might expect to just get the same thing that we saw with alkenes, right? The addition of methanol across the double bond. Now the difference here, though, is that unlike in the case of an alkene, right, where we just now have a new carbon-hydrogen bond, in the presence of, when we're sort of doing this chemistry with, say, carbonyl, we still have some very Lewis basic sites, or Bronsted basic sites, I guess in this case, on that oxygen, right? So we've still got lone pairs there. And so in previous, with the carbon, there's no lone pairs, but in this case, we have lone pairs. And so this isn't where this reaction stops, okay? Because this oxygen can in fact, or those lone pairs can in fact react with more sulfuric acid. Okay? And what's going to happen here now is we're going to get to this compound here, right? What might you guys think might happen now? The water, now we've got water, right, which could be a very good leaving group. Okay? When the water leaves, I'm just going to go ahead and sort of, actually I'll just show it in this way. Right, so we've got this one here. Now we can draw a resonance form of that, right? That's a stable cation because of what? Right, because right next to it, this is actually the minor resonance form. You can actually push those electrons onto there. Well, we can leave it here, yes?
Why is HSO3 minus giving away iron?
Oh, sorry, HSO3H. This is just right. This formed right when we did that. We regenerated sulfuric acid. So this acid is catalytic in this reaction. Okay, so now we're here, right? And now we should all be able to finish this mechanism, right? What do you think the next step might be? Yes, we lost an equivalent of water, but we're in a solution of methanol, right? And so all the methanol that we have now, the methanol can add in, right? Right? And at this step now, what might be the next thing that would happen? We're going to deprotonate it. That could be done again, we're regenerating the sulfonate here. It goes back to the sort of question that was asked earlier. So OSO3H minus can then come and deprotonate this. And the product that we get is that not only have we added methanol across once, but we've sort of now exchanged the hydroxyl with the methanol. So if you look at this reaction, what does this kind of remind you of? So the first step is very analogous to, say, addition, right, across a alkene, right? So this first step up to here is basically the addition of methanol across an alkene. And what's this next step kind of like? Kind of like a substitution, right? So it's kind of it's like acid-mediated ether formation, right? So we've seen how two alcohols can react in acid and form an ether. And so that's basically the second step. So again, this reaction is very analogous to what we've seen in the past. It's ketone, again, ketone or carbonyl rather than an alkene that methanol adds across, just as it would add across an alkene, except that there's some subtle differences that we see. And the second step is simply an elimination. Or sorry, a substitution reaction. Okay, so I'll just redraw this a little bit differently. So the product of this reaction is something called a ketal. And it turns out that ketals are actually really good protecting groups for carbonyls. So as we sort of discussed earlier, sometimes carbonyls, in the same way that alcohols can behave, carbonyls can be nucleophilic, and so if you're going to treat something with a nucleophile somewhere, in the same way that you could protect an alcohol with a silyl group, sometimes you can protect a compound as a ketal. Sometimes the target that you're going after desired is a ketal, so certainly there are, say, for example, drugs that are on the market that are important that have sort of ketal acetal intermediates. Artemisinin, which is a big malarial drug, has this. And so, again, ketals are both valuable in terms of targets that we can make, and so there's some value there in terms of the ones to be a target. But there's also value in terms of this being a method that you could use to protect. Okay, so now I'm going to ask you guys to sort of look at this reaction, and without being too open-ended, there's something that's slightly wrong with my mechanism here. And what is that? That's that all these reactions are reversible. Right? So as we sort of said, every reaction is reversible, and particularly in this case, every reaction here is reversible. And so in the same way that this could be, we can go in this direction, right? I'm not going to go through this. This would be something that you guys might want to do on your own. We can also go in the reverse direction. Okay? How might we take this ketal and convert it into a ketone? What's that? No, I see where your thought process is, but what drives this reaction? This is all under acidic conditions, right? So in order to get everything, you just want to go in the reverse direction. And so these are all reversible in acid. What's the difference here? Is that we're basically switching out, where's our water? Where do we lose our water? Right here, right? So in the forward direction, we're losing water. But in the forward direction, we'd be gaining water, okay? Okay? And so what drives this reaction, this is a sort of a dehydrative reaction. So when we're running this reaction, and it's similar to what we've seen in the past with, say, ether formation or eliminations of alcohols, we're sort of driving it with the loss of water. And it's the same thing here, right? We're driving this reaction usually by losing water, or we just run it in a methanol solution, so there's so much more methanol than water. So at this step, either the methanol can add in or the water can add in, but we've got so much methanol that it sort of pushes the reaction. So now I ask you guys again, if we want to take this compound and go back to the ketone, right? I said this can be a protecting group, right? If it's a protecting group, then it means that you have to be able to go in reverse. So if we wanted to convert this compound into this compound, we would use sulfuric acid and water, right? So now instead of using methanol, you would switch that up with water, right? And so you guys could try this on your own. I'm not going to go through this mechanism. But if you said, say, H, so sulfuric acid and water, you can actually go back to the ketone. And that's so that mechanism, so I've shown you guys the mechanism in the forward direction. I would ask you guys to sort of think about what that mechanism is in the reverse direction. And certainly it's a mechanism that you could be, and that you will be responsible for sort of knowing. Okay? A few more points about ketal formation. Okay? So, yes?
Is this only for ketones or could it be alcohol?
So yeah. So any carbonyl. So any well, yes, technically any carbonyl. You don't see this that much with esters, so where you would have an extra oxygen there. But you could do that as well. It's called a orthoester or something like that. But yeah, I think for your guys' sake, you'll primarily see it with ketones and aldehydes. So aldehydes are, right, if that's it. Okay, so I want to make one point that I hadn't really brought up yet. And that's this idea of hydrates. So you notice in this reaction, we got to this intermediate right here. Okay, so this is a molecule that would be called a hydrate, right? So if we sort of, say for example, we're in a situation where statistically speaking, we had one equivalent of methanol and acid, right? So if you just imagine one equivalent, and then say one equivalent of methanol, and you had sulfuric acid in here. This is just a point that I want to make really quickly. If we did this reaction with an alkene, it would react no problem, right? You would add across that one time. In the case of a ketone, you would imagine getting to this molecule here, which is called a hydrate, right? And so I just want to make one point. The hydrates, this kind of goes back to the sort of enol keto tautomers, right? Ketones are sort of favored. There's a benefit to having carbonyls that I believe has to do with the dipole, but I'm not 100% sure as to why. But certainly there's a strength to carbonyls that when molecules can exist as carbonyls, they tend to like to. So carbonyls sort of represent a sink. So when by and large, for the vast majority of compounds, if you could imagine that equilibrium, it's going to strongly favor the ketone. So that's just something that's important to recognize. That except in very few cases do you end up with this sort of hemiacetal here, or the hydrate. Okay? The only times when you will see it is sometimes in an intermolecular reaction. You'll see it, and in other cases where you say, for example, destabilize the carbonyl. So again, this is a little bit beyond what I care for you guys to have to know. But it turns out that if you have strongly electron withdrawing groups on that carbonyl, so you don't really need to know this, but I'll just sort of show this just in case you come across something similar and are curious about why. This is a molecule called, let me just double check. This is a molecule actually called chloral. Okay? And so on occasion you guys may see like hydrates that are stable. This is like one of the only examples where you'll see that. So if you have sort of water in here, you'll actually end up as the hydrate. So this is chloral hydrate. Okay? And again, this is the sort of exception to the rule. Like, this is one of the very few exception to rule. So again, just in case you're sort of doing reading and you sort of see that there's a hydrate that seems to be stable, it's not that they can't happen, it's just that the vast majority of times they want to be at the carbonyl. Okay? There are exceptions to that rule, chloral and chloral hydrate. This is like a knockout. This is like, I think it's like a knockout drug or something like that. But again, this is the point being that you may see this structure from time to time, and so you may be curious, and the reason is that you destabilize the carbonyl with the electron withdrawal. So that's just in case you guys come across that. Okay. Okay. So this is hydrates, ketal formation. I'm going to show you guys that another reaction that's almost identical to this. Okay. And that's if I'll just give myself some room here. Now, it turns out that if you do this reaction, and instead of using methanol, you use, instead of the oxygen being nucleophile, you use an amine. Let's say R, right? So if you have a primary amine, so this would be a primary amine, again, because it's got one alkyl group and 2 protons. This is also going to react with this compound. It's going to lead to something slightly different that hopefully will make sense to you guys when we go through it. So again, if we go through the same thing we just saw before, right? The first step is going to be protonation, right, of that carbonyl. In this case, now we don't have methanol, but we have the amine. So what's going to be the next step? The amine is going to attack here, right? So the amine has lone pairs. Right, so the amine is going to attack. Okay, what's the charge? The nitrogen is going to have a positive charge on it, right? The next step will be deprotonation of this. For board space, I'm actually going to do something a little bit just to sort of save you guys a little bit of board space. But what's going to happen is we're going to deprotonate this guy, generating the amine, and then just like we saw before, then this alcohol is going to get protonated. So I'm just going to do something here, just it's a little bit more direct. It likely doesn't happen this way, but at least in terms of bookkeeping, you can think about it this way, right? So sometimes if you guys are drawing a mechanism and you're trying to do a proton transfer, you can do that sort of readily, right? You don't necessarily need to show everything.
Seriously.
What's that?
But this is like the last question on the test, right? We could just, that's the last question on the test.
She's talking about the written.
I'm talking about the last question on our exam.
The Ritter reaction? A proton transfer?
Yeah, that was like the last step.
Yeah, no, I mean, this is something you're going to see a lot, right? Protons will transfer fairly readily. Okay, so in this case, now what you're going to be at is this guy here, right? The oxygen's going to leave, right? Okay, and one of the differences here, though, so this is one subtle difference, but it actually makes a rather big difference in terms of what we make, is that now what's going to happen is, again, we sort of discussed this a little bit before with carbonyls, but this certainly is just a resonance form, right? And so there's a resonance form here. Okay, so that's just a resonance form. Okay, and then the last step will be deprotonation, right? So unlike the previous case, the nitrogen is not going to add in here, right? And the reason for that is that the nitrogen can just deprotonate this, and that would be better. Okay. And so the product that you get when you have acid and water is, instead of having this sort of hydrate, you'll notice that the nitrogen has a second extra pair of lone pairs. So again, as we sort of discussed, sometimes these double bonds are important. With the oxygen, right, you couldn't have this double bond, right, because otherwise we would have an oxonium up here, right? So if nitrogen was an oxygen, it would be a positive charge, right? Which is the reason why this wouldn't form with the oxygen case. But in the nitrogen, you can make this double bond, right? And we're sort of our charges are satisfied. So again, this is sort of another reaction. It should be very analogous to the ketal formation, with the exception of the fact that nitrogen can be bonded to 3 different things. Because of that, you can sort of make this molecule called an imine. Okay. Okay. So yes. Say that again. Yes. Oh, that was from up here. Oh, SO3H. I just sort of drew it reverse. Yeah, so again, this goes back to sulfuric acid, and this is what we're going to see a lot, is these acids, it's catalytic. So you sort of take the sulfuric acid, you react it, you regenerate the acid, and it's not necessarily that you regenerate sulfuric acid like you could imagine other things deprotonating this. Like, it gets a little bit more complicated, but I'm just trying to keep this way for bookkeeping. But you could imagine this carbonyl reacting with that, and then you would have this compound, right? So when we're dealing with these acid-catalyzed processes, there's lots of possibilities, and I'm just going to try to show it to you guys in the way that at least bookkeeps everything. Okay, so, all right, so now I'm going to ask, we're going to go through another very similar reaction that's just slightly different in one extent. So if you take this and it's a primary amine, you're going to get to the imine, okay? And so now we're going to go through a mechanism and try to predict what's going to happen. Okay, guys, quiet. Quiet down, please. Okay, so now what we're going to do is we're going to go through the same thing, but we're going to look at a secondary amine. Okay, yes? This is an amine is a nitrogen-containing compound. The imine, IMINE, that I drew previously, is a carbon double bond to a nitrogen. So it's kind of like a carbonyl, but instead of an oxygen with a nitrogen. Okay? So now, instead of the primary amine, so it's confusing because they sound amine, imine. It gets even more complicated. There's like imides, amides. So yeah, they didn't really do too good of a job of making them sound different. Okay, so let's think about this with a secondary amine. So now instead of it being NH2, it's NH, okay? And again, I'll just go through the sort of the mechanism. Right, so we're going to get to here, as you guys have seen in the past. Right, we're going to have that react with the carbonyl. Right, this is exactly what I drew before. I'll do that proton transfer that I did before, right? So I'm going to take this, grab that nitrogen, okay? Right, the next step is going to be, this is positively charged, the next step is going to be that we're going to leave the water, okay? And I'll just to make it quick, I'm just going to sort of go right to the major resonance form. Okay, so this is the major resonance form. So now what's the difference between this one and the one that I showed previously? We have two R groups instead of a proton, right? And so protons, those can exchange quickly. That's why we say proton exchange or these other things. But sort of exchanging out an alkyl group, having something attack an alkyl group is a little bit sometimes more difficult. Certainly it happens. We see this in substitution reactions. But in this case, that's not going to happen. But the imine, or I guess it would be an iminium, it doesn't like having that positive charge. But instead of a second nitrogen adding in, something slightly different can happen here. Okay? And what's going to happen is that we have this sort of sulfonate. So I'll just do SO3H. But again, it could be other aspects. What's going to happen is something that's very similar to an elimination reaction. So these mechanisms that I'm going to draw are very similar to an elimination, except that we're just going to break this double bond instead of a single bond, right? So it's kind of very similar to an elimination reaction. And now what we get to is a compound called an enamine. Okay? All right, so again, if you have a primary amine, you're going to get to the imine. Amine, you're going to get to the imine. If you have a secondary amine, you're going to get to the enamine. And again, where it differs is we can't simply pluck off that R group. So what's going to happen is there's a proton over here that we can grab, and that's going to allow us to help that double bond through the enamine. Okay? Okay? Yes?
Primary amine, you said you get to the...
That's the one that I just showed previously. That's the one where we'll get to it'll stay at the double bond, right? So if R is an H, right, we can deprotonate that and we can just be at the imine. But because there's an R group here, it's sort of not, now you're not going to deprotonate that, you don't have the proton there. So what happens is it goes after this proton, right, and you get to this compound.
Just resolve the positive charge.
Yes, exactly. So we don't want to set the positive charge if we don't have to. Okay? All right, so, and again, in the same way with the imine and the enamine, you could imagine that this is sort of driven in the same way as before by the release of water. And so, while in this case, this sort of reverse reaction is a little bit more sluggish, certainly you can go in the reverse direction as well by sort of showing water. But I think it's just sort of important that you guys know these mechanisms. They're a little bit more involved than some of the mechanisms that we've seen in the past, so they're certainly good ones to really practice and get down, because there's nothing in these types of reactions, I don't think there's anything that's too fancy, but they are a little bit longer. And so from that extent, I think that they are good ways to sort of think through the mechanisms, or think through arrow pushing to get to that sort of final answer. So these sort of represent a medium challenge mechanism question that I think can be helpful for you guys. Yes?
Do we have to memorize the imine, enamine, like the names of all of them?
No. I mean, the names that you guys will hopefully hear us say from time to time, imines and amines, I mean, you can learn them, but I wouldn't stress out too much about them. The ones that are going to be more important are the carbonyl-containing ones. So aldehydes, ketones, esters. Those are a little bit more important. Certainly, I'm not saying that that's not important, but so learn it if you can. But I don't think that that's going to be it's going to kill you if you can't remember them. So, okay? Yes?
Yeah, so my question basically is the reason that attacks, even though it's a conjugate of a strong acid, is it because it creates an alkoxide? Is it like an alkoxide? Why would it attack the elimination?
An alkoxide?
Yeah, I don't know. That's why.
Oh, it's just a conjugate base.
Yeah, but isn't the conjugate base weak?
Oh, yeah.
So then how's it elimination? Is it heat?
What's that?
Is it heat? Like how is it eliminated?
It's just that this is the desired product. Yeah, I mean, this is where it goes. I mean, again, we see this from time to time. You know, you don't necessarily have to show this one. I mean, think about it like an E1 elimination.
Right.
You don't need a strong base for no. You know, this is not too dissimilar, you know, from an elimination reaction when we're trying to eliminate water. Or sorry, if we have an alcohol and we're trying to eliminate that to generate an alkene. It's very analogous. So you don't always need. Yeah, and again, and so you'll see reactions are often either in the presence of a strong base, or they're often in the presence of a strong acid. You can't sort of mix and match both because they'll react together. And so, you know, the idea here is that you sort of have a positive charge, and you're sort of shuffling that around in terms of the mechanisms. Okay, so
Wait, I have one more.
yes.
When it comes to any of these problems, if you don't specify how many equivalents there are of each, so we just basically, we're free to read or use many. I should just get
Yeah, I mean, I'm not sure. So if
if you don't specify that the problem is exactly two equivalents of whichever.
well, this is usually yeah. I mean, usually in this case.
Yeah, not the problem, the one before the
Usually it's a solvent, right? So usually the methanol is solvent, and so there's a gross excess of it. So in those cases, we're not usually relying upon equivalencies like we might have been with, say, alkynes, right? With like alkynes, it's like, okay, I add bromine across. I add once if I have one equivalent, twice if I have the other equivalent. Here, again, everything's reversible, so we're really driving this reaction. And one of the ways that we're driving this reaction is sort of via Le Chapelier's principle, right? You sort of put emphasis on one side. So if you're trying to push the equation to the right, you sort of add an equivalent, you know, you increase the concentration of stuff on the left. And so that's kind of what's going on with those previous ones. So if you're trying to make the methyl ketal, you use like just a ton of methanol. So you just use it as a solvent. Okay? Okay. So there's imines, there's enamines. Okay. All right, so this is it for this type of stuff. Again, condensation, this is sort of condensation chemistry. These ones that I've shown so far in the sort of first half of the class has been condensation chemistry. Now we're going to go on to some that are more not acid mediated. Guys, can you quiet down, please? Thank you. So what we're going to discuss now is sort of oxidation reductions. Okay, and so what we're talking about here, by and large, is sort of whether we're adding hydrogen across the double bond or whether we're sort of going in the reverse direction. So this would be an oxidation. This would be a reduction. And we'll get to the oxidations later on. It's a little bit more mechanistically difficult, but the reductions are actually something that you can really make sense of, right? Because if you look at this compound here, right, we've sort of seen in the past how we might reduce this. And one way that you might do that, I'm not going to really discuss this too much, might be analogous to how we did it with alkenes, right? So if you use, like, there's certain metals, and certainly not all metals, but there are certain metals that you can use where you can take hydrogen gas and that metal and you can actually reduce carbonyl double bond down. But I'm not going to really discuss that one because that's not usually that common of a reaction to use. The more common way that people do reductions are with through a process that might make sense. So I'm just going to right now just show it mechanistically. But what we use is hydrides. So you're going to see all these things called blah, 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 hydride. Okay, and so what a hydride is, right, is H minus. Okay, so that's a hydride. Okay, and so we'll get into some of the hydrides later on, but you'll see this. It'll be something hydride. Mechanistically, you can rationalize this through what we discussed before, and thinking about the hydride being a nucleophile. Okay, so if we, as we just saw before, if this is going to attack, right? If we have a hydride attack, this is sort of what we saw before, right? We're going to add that hydrogen into that. Right, we're going to end up with that alkoxide, and as I sort of said earlier, you're at this alkoxide, but at the end of every reaction, generally what we do is a workup, and that workup is generally dumping it into water and then extracting it, as you guys have sort of done extractions in your laboratory courses. So the sort of next step is you do a workup, and the result is that now you have the alcohol. So formally, we can think about reducing a ketone, right? In this case, as I've drawn, adding hydrogen across in a sort of a two-step process, right? So addition, so this is just nucleophilic addition to the carbonyl, and this is just sort of acid-base reaction, right? This is going to react with the water. Yes?
If hydrides are very strong bases, why wouldn't they attack the hydrogen beta?
And make it enolate? So it could, not depending upon the base source. So the bases that we're going to show are actually good nucleophiles. This gets into something called sort of base versus nucleophile. So this is the sort of idea of whether something's going to behave as a base or whether it's going to behave as a nucleophile. Again, you can sort of go back and look at in your book in terms of substitution versus eliminations and things like that. But I think it's important to recognize those discrepancies. But what we do is we have ways to sort of make things better nucleophiles. And so we'll see there's this sort of thing called soft and hard. So there's sort of soft nucleophiles and soft anions that are more likely to react. And so in these cases, is what you'll see is I guess they would be considered soft, but yeah, but they could be bases, right? And certainly if you have some of these hydride sources that we'll see, if you have an alcohol around, say for example, they'll certainly deprotonate that alcohol. Meanwhile, we also have ways that we can deprotonate that, but that's something that I think you'll learn next semester. Okay? So do you guys see this? Yeah? Yeah, you usually, when you're done with the reaction, you just take your solution, you pour it onto water, and so there's kind of like we said similar before, like Le Chatelier's principle. So the pK of water and the pK of an alkoxide, water is a little bit more acidic, but that's what you sort of do is you just charge it with a whole bunch of water. And so what you get is like a solution of hydroxide and water. And sometimes we'll have other things in there that will quench it. But the point is that there's a workup that quenches that, and there's different ways that you could do that. So sometimes you'll buffer the water with some slight acidic source in case there's other problems. But I don't want to get into the details of that. The important point is that you do the workup, and you get that second equivalent of hydrogen, right? So again, I think the reduction, right, unlike the reduction with an alkene, right, where we have hydrogen and a metal, you can actually reason the chemistry of a carbonyl with, I think, the chemistry that we know, right? So it's just a sort of substitution-like reaction, nucleophilic addition into a carbonyl, followed by sort of acid-base mechanism that you would imagine during that workup. Okay? Okay, so there's a few different types. So again, I talk about the different types of hydrides, and so all these hydride sources that you'll see. So you can imagine, so back to your sort of question, these reagents that people have made are sort of specified towards this reaction. People have spent a lot of time developing them to make sure that they're selective towards this. So just taking a carbonyl and treating it with sodium hydride, for example, might not work that well, right? And so there's other reagents that people have developed that are more likely just to sort of add into that carbonyl. So I'll go through these and where we will sort of use them differently. Okay? So the first one is the big guns. So the big one is lithium aluminum hydride. So this is the one that's like our sort of strongest reducing compound. So this will reduce any carbonyl compound at all. In fact, it's the structure of it is lithium plus AlH4 minus. Okay, so it's an aluminum hydrogen bond that's actually serving as a nucleophile. But again, you guys can just think about it as an H minus because I think that makes more sense, at least for you guys. And so this is the strongest of them all. So this is the strongest. Okay, so I'll just go through some of the terminology of different carbonyls here, and this is going to reduce them all. So again, ketones. So this is a ketone. If you react, so this is sometimes abbreviated LAH. So that's what I'll just sort of say just for board space, but LAH. Followed by the workup, what this is going to lead to, again, is is addition across that alkene, or sorry, across that ketone. Aldehydes, right? So this is an aldehyde, right? So aldehydes are actually even more reactive than ketones. There could be, you could think about this from a steric standpoint. There's actually an electronic standpoint as well, and it has to do with stabilizing that positive charge, right? I'm actually going to show you guys that in a second. It's probably worth showing. So again, you treat this with LAH. What's going to happen is you're going to react, and now what you end up with is mechanistically the same thing. Okay? And the other compound that we'll discuss, so somebody was asking me about terminology, so I think these three are sort of worth talking about. There's actually a fourth, I guess, so this is a molecule called an ester. Okay? When R is a hydrogen, what is that called? If R is a hydrogen, carboxylic acid. So I think these terms are worth knowing, okay, because we will discuss some of the differences in reactivity of these. And so these are terms that I think are worth knowing. I'm going to make some space here because let's go through that one. It's actually a little bit different because in this case, what happens, let's just go through the mechanism real quick.
What about the oxidative
Hmm?
What about the oxidative
We'll get to that. We'll get to oxidations. Yeah. So reduction, and then we'll go back to oxidation. Okay, so let's think about what would happen with an ester. I just want to sort of show this mechanistically. Okay? If we do this reaction and we treat this with a hydride source, right? What's going to be the product that we're going to get? Or at least the first step in it. Right? So we sort of discussed this earlier. So this is sort of an alkoxide, so that's with the hydrogen adding in once. And what might you imagine might happen here? So we just sort of said this is not that stable. These molecules like to go to carbonyls if possible. Okay, so can you guys see mechanistically how this might, not really a resonance. Yeah, it's sort of like we're going to lose this. And it's kind of like it's sort of like an elimination if you can imagine that's already sort of deprotonated. Right? And what this is going to get to now is this aldehyde. Okay? And as I'll discuss in a minute, as I sort of said just earlier, and I'll go into a little bit more details about why this is the case, but aldehydes are some of the most reactive things we have. So the minute that we generate this aldehyde, a second equivalent of hydride is going to add in. Okay, so this isn't even a stoichiometry issue, right? This is right? You're going to have that alkoxide, and then following the workup, so we're going to get to this alcohol. So now, as I sort of said, this aldehyde is going to react instantly, right? And so this is an instance where lithium aluminum hydride is going to react all the way down. You can't use just one equivalent and hope that it would go. More likely, if you could control the equivalency, right, what you would probably get is a 50-50 mixture of this and none of this, right? Because the moment that's going to react much faster with the aldehyde than the ester. So the point is that if you take this molecule, if you take either an ester or carboxylic acid and you treat it with LAH, you're going to go down to the primary alcohol. Okay? So this is important, right? This ester is actually more or less reactive than the aldehyde, so it's just going to sort of go all the way down. So I want to really quickly discuss why that's the case, because I think it actually, you guys sort of know enough at this point where you can at least rationalize if you get confused about the relative reactivity. I think we can think about this. I'm going to go ahead and erase this. It's on my website. Okay, so in terms of relative reactivity of carbonyls, yeah, it's kind of, relative reactivity. It's got a nice... So the most reactive are aldehydes, okay? So aldehydes are most reactive, okay? So most reactive. Okay? In terms of these three, ketones are the next most reactive. Okay? And at least in terms of these guys, you know, you might be able to make comparisons with others as we sort of move forward. But esters are, again, just in terms of these, there are others that are less reactive, but at least in terms of these guys, we'll say these are least reactive.
Then what about the carboxylic acid?
Yeah, so the carboxylic acids, so I guess I'm sort of including carboxylic acids in there with esters. As you'll see, carboxylic acids are actually a little bit slower to react than esters. And once I sort of explain this, maybe you guys can sort of explain why. Okay, and so the reason here in terms of reactivity is we sort of mentioned, a lot's sort of coming together here, right? We talked about how carbonyls, by and large, like to be carbonyls, right? You like that carbon-oxygen double bond, right? And then we sort of discussed this one instance where it wasn't, and we said that's because you're sort of destabilizing that carbocation, right? By having an electron withdrawing group nearby, okay? And so if we imagine that being a delta positive, and we think about this resonance form, right? The more stable the carbonyl, right, the less reactive it's going to be, right? So let's just think about that. The more stable the carbonyl, the less reactive the carbonyl. Does that make sense?
Yes.
Thereby, the less stable the carbonyl, the more reactive.
So a tertiary structure
So that's what we're going to discuss. So let's think about how each of these different compounds stabilize that resonance form. Okay? And thereby stabilizing that resonance forms, stabilize that carbonyl. Does that make sense? Okay, so here certainly there's a resonance form, right? They're all going to have that resonance form. So we can take that oxygen out of the picture and really just think about this impact here. Okay. Now, if we were to compare all of these, right, and let's take that oxygen out of the picture, this would probably be the ranking that you guys would assume, right? So this would kind of be like a tertiary carbocation, right? or secondary, whatever you want to call it, or primary. I'm just assuming that that's sorry, you're assuming this is a second. Let's pretend that that's a carbon. Okay, so that's a secondary carbocation, right? That would be a tertiary carbocation. And then this one would sort of be a tertiary carbocation, but why is it even more stable than the other one? Because you would have those lone pairs have a resonance form there. Okay, does this make sense? Okay, so then again, there's the sort of explanation for the relative reactivity. Okay, I'm going to jump ahead. So this is one of the things that I actually jump ahead because I think this is a place where you guys should learn it, even though it's technically for next semester, but I'm going to teach it to you now because why not? So the ester, no, this is where you should learn this. So you're going to learn it here. So here's an ester, right? And you're going all the way to an alcohol, right? And you'll understand why this is where I teach it. And we're learning all these different reducing agents. So lithium aluminum hydride will react with this. It will react with all of these, and these will be the products that form. Okay? The other one that you guys will see, so I'll just show you guys all the different all the different hydride sources here. Okay? The other one that we have is sodium Okay, so this is very similar structurally. Na plus BH4 minus. Okay, this is not as strong as lithium aluminum hydride. Okay, and it turns out that this sodium borohydride will reduce ketones as you guys would imagine, aldehydes. If it reacts with ketones, it will react with aldehydes as well. But the thing that it won't react with is carboxylic acids and esters. You really have to push it to work with esters. I don't think that you can get it to work with carboxylic acids at all. So esters, we'll just put an X there. It doesn't work that well. You can, in fact, get it to work, but you've really got to push it to react. But the important point here is that, let's say you have a molecule, right? There's a selectivity issue here, so why do we have this? Well, let's say you had a molecule, right, where you had, say, an aldehyde and an ester, right? And you only wanted to reduce the aldehyde and you didn't want to reduce the ester. This gives you an element of selectivity that's important. From a practical standpoint, sodium borohydride is also very easy to work with. Lithium aluminum hydride will actually ignite spontaneously. And so handling it can often be a little bit more challenging. So sodium borohydride is a little bit nicer to handle. That's one of the reasons why people like to have it. But it also gives you this ability, for your guys' standpoint, you're not actually going to be in the lab using it. So you might say, well, then I'm just going to remember LAH. Well, sodium borohydride might be valuable for you because there might be an instance where you want to reduce, say, a ketone or an aldehyde, and you don't want it to touch an ester or carboxylic acid. And so for your guys' standpoint, the sodium borohydride might be useful from a selectivity standpoint. Okay? The last one, so this is in your chapter, but this one you'll have to read ahead. And this is a compound called dibol. Okay, and dibol it's a hydride source. Okay, it stands for diisobutyl aluminum hydride, and so I'm not going to go through the exact structure of it, but instead of it being, so these are isobutyls. I'll just put R2 to sort of simplify it. The important point is, and there's actually a bunch that are kind of similar to this, but the difference between this one, right, and the ones that we saw before, this one are aluminum, is that the dibol is actually, it's not that it's bulky, it's not charged, right? All these other ones had BH4 minus or ALH4 minus. This one, dibol, is actually, it's aluminum with 3 things bonded to it, right? So it's kind of like BF3. Right, so it doesn't have a full octet. The others, the aluminum and the boron, both had full octets, but they were negatively charged. Dibol doesn't. Okay? And what that allows you to do, and where this is important is with esters. Okay? The mechanism of a dibol reaction So what kind of molecule, at least in terms of first approximation, what kind of molecule is dibol? Is it an acid? Is it a Lewis acid? Is it a bronzite base? It's a Lewis acid. Why? Because it doesn't have a full octet. Absolutely, right? So what's the first reaction that you think is going to happen here? Exactly. The lone pair on oxygen is going to attack the aluminum. Okay? And now we have our hydride. Okay, so now, so sort of this activation, if you will, of the dibol, right? So the dibol, once you now add into that carbonyl, now what you have is the hydride. Okay? And what's going to happen is that hydride is going to deliver itself into that carbonyl. Okay? Okay, so this is important. Now, the mechanism is actually a little bit more complicated than this, but this should explain what happens. Oops. Okay, so now we've got that hydrogen there, and now we've got this OR. Okay, now it's a little bit more complicated than this, but this kind of tells you something, right? Previously, we had those electrons dump down and kick off, but now we don't have that ability, right? We can think about these, again, we can think about those lone pairs even being tied back into that aluminum, right? So those electrons are not going to want to break down. You're not going to, and again, it's a little bit more complicated than this, but this sort of should help explain it. You're not going to break down at this point, okay? So you're stopped there, okay? And then what happens is you work up this reaction, okay? So you take this reaction, you treat it with water and everything else, and when you treat this with water, the water adds in, you sort of break this down. So what's going to happen is, we can go through the mechanism, but the point is that the important point is that once you have water in there, and it's a little bit more involved, I forget exactly what the conditions are, but you'll actually hydrolyze that off. So I'm not going to go through the details of it. But you'll actually hydrolyze this off, get into that negative charge, and you'll kick down. When you do that, you also quench all the excess dibol, so there's no more dibol there to do the chemistry, right? And so what dibol allows you to do is go directly from the ester to the aldehyde. Okay, so that's why I think this is important to learn here. We sort of learned how to go all the way to the alcohol, and why it goes to the alcohol. Well, why not now show you guys how to just stop at that aldehyde? Yes?
This is two molecules, or just one? Split the molecule into two?
What do you mean?
Because we started, we had two molecules, two oxygens, and then we had one oxygen, one last workup.
Oh, the workup, it's with water. So the mechanism, you could just think about it as a sort of water adding in and kicking that off and then breaking down.
And that molecule split into two, or it's still one molecule?
Oh, this will go down and you'll lose the OR. Yeah, just like before. Just like the elimination that we saw before with LAH. So if you think about the water helping you get to the O- and then that breaks down. But again, you generate that aldehyde, but there's no more dibol in there. So you're good. Okay? All right, so we've got about 6 more minutes left. So we've really learned 2 things today, right? We sort of 3. We sort of learned about the general overview of carbonyl reactions and how carbonyls behave reactivity-wise. Then we sort of learned about dehydration reactions, sort of acid in the presence of carbonyls, where you have another alcohol or an amine, right? And that does this sort of condensation chemistry. Then we've sort of learned about how we can reduce down different carbonyls, which is effectively just the addition of a hydride into there. And so again, all these are sort of hydrides, so diisobutyl aluminum hydride, sodium borohydride, lithium aluminum hydride. That's why I was saying blah, 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 blah hydride. They all can sort of, at least mechanistically, be thought of as H- adding into that. Again, that's not how it actually behaves, but I think from a mechanism standpoint, you guys can rationalize the mechanism and understand the chemistry through that. Okay? So now what we're going to discuss is oxidations. Yes?
You said this activity for aluminum is similar to the boron fluorinization?
Hydroboration in a way. Yeah, how I sort of first went through it, kind of. Yeah, that's not really how the hydrogenation works, right? But yeah, when we first sort of had to add in the hydride add, yeah, it's very similar to that. Okay, so the last thing we want to know is now we know how to get to the alcohol. Now the question is, how do we go the other direction? Okay, so in this case, what we're going to do is we're effectively going to pull out equivalents of hydrogen. So it's going to be sort of minus H2. Okay, we'll start with, actually, I'll start with ketones. Okay, so if you have a ketone, you pull out 2 hydrogens. Again, these 2 hydrogens. Or sorry, if you start from a secondary alcohol, you're going to get to a ketone, right? And so this is a reaction that's mechanistically, I would say that this involves transition metal chemistry, so you're not going to be responsible for understanding the mechanism of this, but we'll sort of show you guys how it's done. Okay, so the way that you go from a secondary alcohol to a ketone, okay, is you use something that's called Jones reagent. So this is a very strong oxidizing reagent. Jones reagent. And so what it is it's a high oxidation state chromium. Okay, so it's H2CrO4. So this is actually the active part of Jones reagent. I think technically what Jones reagent is sulfuric acid with chromium trioxide, and sort of it reacts and generates sort of this compound. So it's this acidic reagent which ends up getting you to this sort of ketone. I'm just trying to think of, we've got a couple more minutes left. Turns out that chromic acid is a very strong acid. So actually, I'm just going to sort of show these, and I'm not going to go over the mechanisms, but I'll try to put them in perspective. If you have, this is sort of the lesson here with a lot of this. If you have an aldehyde in here, or sorry, if you have a primary alcohol and you treat it to Jones reagent as well, what's going to happen is you're going to get to the aldehyde, right? And the thing with the aldehyde, right, is that then now we're saying we're sort of going to lose 2 equivalents of acid. But one of the important things to recognize, and so this will be a mechanistic, this is about as far into the mechanism as we're going to go. Chromic acid, you run these reactions in an aqueous solution, so there's water around. Okay, so there's always water in this reaction. And so what happens is when you get to the aldehyde, you can actually, again, this is sort of a minor compound, but it turns out that it's important in terms of the oxidation. What you get to is, and again, this is not, obviously it would favor this way, but you can get to this sort of, oh, wait.
Try out.
So that's, yeah. So again, you just add water in there, right? So the proton, I accidentally did that. Okay? And now you can sort of see that you can lose hydrogen again. Right? So here now you lose a second equivalent of hydrogen. And so when you have Jones reagent and you're in the presence of a primary alcohol, what you actually do is you oxidize all the way up to the carboxylic acid. So the important point to note is that there's this hydrate. Okay, all the reagents that go into it are water soluble, so you have to sort of do this in the presence of water. How might you now stop at the aldehyde? You do something that doesn't have water in it, right? And so what the other thing that they came up that was sort of created is if you want to get to the aldehyde, and then I'll stop after this, you need to prevent it from going to this hydrate. And so what they use is something called PCC, which is pyridinium chlorochromate. The important point to this, though, is that this is soluble in dichloromethane. You can run this over molecular sieves, so you can keep this very, very dry. never get to the hydrate, and if you prevent it from going to the hydrate, then what you end up doing is you get to the aldehyde, you can actually get there. Okay, so the important point about PCC, again, structure of it, I don't really care that you know it or not. The important point to sort of remember is that it's a chromium reagent that's very similar to Jones reagent, except that they've sort of tweaked it a little bit so that it can be soluble in an organic solvent. You don't have to have it in the water, in which case now you don't get to the hydrate, and now you can get to the aldehyde. Okay? So with that, I'll see you guys on Thursday.
Why are you so